Okay, piecewise functions. Actually here. Some situations are described by two or more functions. For example, the table below shows the value of a particular investment over time. So, what's happening with this investment? At least initially. Chose wisely, yeah. So, how much is it increasing by? $200, right? So it's like plus 200. Going from here to here. Well, okay, let's do this. Let's say this is 1,000 plus 200. This is 1,000 plus 200 times 2, right? So it's been 2 years. So 200s, 1,000 plus 200 times 3. 200 times 4. Okay, now do we add 200 here? No. Okay, so what's going on now? How much do we increase by? In actual dollar amount, how much do we increase by? 140, good. Because we're not using calculators in this class, right? So you better get used to it. And then we increase by, is it another 140? No, it's a little bit more. So likely we're increasing by a percentage, right? 7%. Okay, so then this is going to be the 2,000 times 1.07. So the amount. So at this point, it's going to start to grow exponentially, right? So what we might have had is like a simple interest bond, and a simple interest bond just would pay the same amount each year. Pretty darn good rate. It's like 20%. So, you're not going to find that. And then we're moving to compound interest. So we have part of this is, so for the first 5 years, the investment increases by the same amount each year. What kind of function increases by the same amount? If I plotted the points linear, good. So a linear function could be used to describe the value of investment for the first, how many years? 5 years. During the last 6 years, the investment does not increase by the same amount, but rather increases, what fancy word goes in there? Exponentially. Therefore, what kind of function can be used to describe exponentially increasing? Exponential, good. Yeah, you want to give it away by saying exponential. So therefore, an exponential function can be used to describe the value of the investment during the last 11 minus 6 years. So write an equation in the form v of t, well, they should say a function, that represents the value of the investment for the first 5 years, where v of t represents the value of the investment after t years. Okay. So what is v of t? V of t equals something t. What's the something? 200t plus 1,000. Right? It's always good to try it out with a value or two, just to check. Okay, if I put a 1 in there, I get 1,200. That's good. I put a 0 in there, I get 1,000. I put a 5 in there, I get 2,000. Write an equation of the form v of t equals a times b to the t that represents the value of the investment for the last 6 years, where v of t, etc., etc. Okay, so what's a? 2,000, right? It's our starting amount, starting with 2,000. What is our rate of growth, or our base of the exponential function? 1.07 to the t. Okay, so far so good. We can express the value of the investment for the entire 11 years as v of t equals, right? So we're just going to write two separate functions and stick a domain on them, right? So, well, if you're between 0 and 5, then we've got the one function, which was 200t plus 1,000. And if you're between 5 and 11, now notice the 5 can't be greater than or equal to on both of them, right? Because at 5, it's between 0 and 5 inclusive, and then not including 5. So any amount of time over 5 years, but up to 11 years, was the 2,000 times 1.07 to the power of t.
It shouldn't be t, it should be t minus 5, shouldn't it be?
Right. Not just t, but t minus 5. Because we're using t to be the number of years, and it starts in year 6, right? Yep.
No, but it says it asks you to write the equation for the last 6 years, not the equation in general for whether it's.
Yeah.
So wouldn't it be just 3?
No, actually, we got to go back and change that. It's going to be t minus 5, right? It says it is for the last 6 years, but we got to start with year 6, right? We're going to have to make t 6. So then this needs to be t minus 5, right? So that it stands in for the chart. You say, well, what is it in year 10? Okay, then you say, okay, it's this. Now this doesn't apply to year 10, right? It's the first 5 years, but this is 6. So t would start at 6, and we need 6 minus 1 to say we're just doing 1 round of interest and then 2. There's a bit more accuracy. So the value can be represented by two different functions, each function with a distinct domain. Okay, that's the key, distinct domain. This is an example of a piecewise function. Number 4, two piecewise, how are we doing on time? Okay. Two piecewise functions that involve the same functions are given below. So we have f of x is negative x plus 1 and x squared minus 1 and x plus 1. But with different values for the domain. And g of x is the same three functions, but so let's take a look at what would f of negative 4 be? So you have to figure out, okay, which function am I using? Which one, where is negative 4 in the domain? Which one am I using, and what value do I get? Toss out a value. The number?
5.
5. Okay, so you say, oh, okay, I'm using this. So this is when x is less than negative 2, I'm using this function. And so it's negative negative 4, which is 4 plus 1 is fine. What about f at negative 2? What's the value? 3. So which function do we use? Top, middle, bottom?
Middle one.
The middle one, right? Because that's, remember, this just says x is less than negative 2. This is negative 2 is less than or equal to x. So this includes negative 2. This doesn't. F of 0?
Negative 1.
Negative 1. And f of 2?
3.
It would be either way, right? But yeah, which one did we use?
Middle one.
The middle one. Although if you use the bottom one, you'd still get 3. But okay. G of negative 4. $15. Like that. Any disagreements? G of negative 2.
3.
3. G of 0.
1.
And G of 2. 3. Okay. Sketch the graph of each function on the grids below. All right, so we've got some points that we can use, right? We start with those points, and then just sort of figure out, okay, now where do we go from here, right? Like, how do I draw this function? All right, so, yeah. Okay, I'm going to have to shrink this a bit, right? So we can see. So let's go to view, zoom, let's do. Perfect. Okay, so we got some points. This will be F, I guess, and that'll be G. So, are you guys? Oh, it's split on the page, isn't it? Oh, that's kind of bad. All right, but you can look up here so you can see this, right? And while we're sketching these. Okay, so, what does it say below? No, nothing much. All right, so F of -4 is 5. Oh, it's a different color. F of -4 is 5. F of -2 is 3. F of 0 is -1. And F of 2 is also 3. And so now the question comes up, what do we do? Well, okay, we've got this thing here which says when x is less than -2. Okay, so when x is less than anything out here, so what kind of a, how am I going to draw this? What do I do from here out? Just a straight line, right? This is just linear -x plus 1. Sorry?
Would it be a non-shaded dot because it doesn't touch it, or is that because it does touch texture?
Right, so we have to say, but the value is 3 for both of them, so yeah, technically this part, oh wait, that's G, negative much. So what would it be here? -2 squared is 4 minus 1 is 3, so it's still going to be 3 there.
So in that situation, what would you want to do?
Well, so it's kind of an open dot for this guy and a closed dot for this guy, so it's just going to be, yeah, it's just going to be a dot, right? Like, it goes through that point and it's that value. Yeah, that'll come in, I think, over there a little bit where there may be different values. Okay, between -2 and 2, we've got x squared minus 1, right? So we know what that looks like. It's just a parabola. Okay, so just x squared, 1, 2, 1, 2, 3, 4. So, okay, it's just going to be, can't see him. I'm shadowed. Okay, so that's x squared minus 1, right? That's just the graph of x squared minus 1 between there and there. And again, all right, so what's happening at 2? That's 3 and that's 3, right? So yes, there's kind of an open dot for the one and a closed for the other. And what are we doing? X plus 1, so just going to go like this, right? Okay, so this is f of x. Now, let's do g of x. Okay, g of x. So, okay, we've got some points we can plot. Well, not the 15, right? But g of 2 is, sorry, g of -2 is 3. G of 0 is 1. And g of 2 is 3. Okay, so what do we want to do for, I guess we do, just go top down, really. I mean, you can work them in any order. But from -2 to 0, we have -x plus 1. Okay, so from -2 to 0, this is just going to be a straight line here, right? Okay, and I mean, you can always throw another value in. You put a -1 in there, you go 1 plus 1 is 2. It's okay, yeah, straight line. This is our parabola, and where does it? Oh, so it kind of goes off on the ends, right? I mean, to the left from here, this goes parabolic. And to the right from here, this goes parabolic. And between 0 and 2, again, we've got another straight line. Okay, good? Yeah. So f of x and g of x involve the exact same functions. Are the graphs the same? No. Why not? Yeah, the domains are different, right? So they're the same functions, but the domains are different. All right, good place for a break, right? Had this for a while. Okay, I don't want to say done. I want to say pause. Okay, so let's give number 5 a try. State the value of, and then plot those points and see if you can graph the function, and then check it with the neighbor, and we'll be back in a moment with stuff filled in. Okay, so we've calculated a few values, and I've plotted those values on the grid, and now we're going to draw the graph. So when x is less than -1, it's just 2x. So this is just going to be 2x, which this is, up 1 or up 2 over 1. And so this guy will just go like that. Now, between -1 and 3, we've got x squared minus 3, right? So what shape is that? It's going to be a parabola, right? X squared minus 3. So 0 squared minus 3 would just be minus 3. So we're going to come down here, come up, and get to where? Okay, so if this included 3, what would the value be? 9 minus 3 would be 6, right? So we're going to get up to 6, but we're not going to be at 6, right? Because that's not included. 3 is not included. And then here, this is just -x plus 2, which is just going to be a straight line down, right? Slope of -1. And there we go, straight line. So at 3, we have this point is not included, but this is the point where. So is this function continuous? No. Why not? So, switch back. No, because so if a function were continuous, how could I, if I was drawing, okay, if I'm drawing a function with a pencil, what's the difference between continuous and not continuous?
Raising the pencil off the paper.
Yeah. So if I have to raise the pencil off the paper and move it, then the function is not continuous, right? If I can continue to draw the function, think of a sine function, right? You just go forever. You never have to lift the pencil off the paper. That's continuous. Okay. So this is not continuous. The graph has 2 unconnected parts, right? The graph has 2 unconnected parts. Were the other guys continuous? Like on the other page, the f of x and g of x? Yeah, we could draw them, right? Even though there was that point, right, where we were saying, wait a second, this doesn't belong to that graph. So open circle there, but we got a closed circle right on top because it does belong to the other graph. So we wouldn't have to lift our pencil there. We wouldn't say, oh, that doesn't belong there. We say, oh, but this point does, so. The graph of that is almost the same as the graph of f of x, but not quite. To show the functions are not the same, where would you evaluate the functions? So, can we see them both? Oh, hang on, shrink. View, zoom, 25. Okay, so what's different between these two? So, is this the same as this? That, same, different? Same, nope, different, where, why? Okay, that includes that doesn't, okay? How about these two? Well, again, so we've got the point -1, and also, so it's in here, right? This is strictly less than down here, and this is strictly greater than here, and this is less than or greater than. So what points would we want to evaluate it at?
-1 and 3.
Yeah, -1 and 3, right? Because those are the points where the domain changes, right? All right. Whoops. Wrong one. To graph piecewise functions on some calculators, which you don't get to use anyways, but if you did want to, it may be useful to change from connected mode to dot mode. This will eliminate any connecting lines the calculator graphs which should not exist. I think the newer firmware takes that out. So I don't think you'd have to worry too much with the newer firmware, right? And then this is how you could graph it, which I guess it's asking us to do. So let's graph it. Excuse me. Okay, so having entered this into the calculator, and we don't need to, this particular calculator, which is the 84 color, but I think the 84 pluses with newer firmware also have this, so you don't need to change from connected to dot mode. And then we just hit graph. And there's the graph. And does that match with our graph from whichever one it is we were graphing? What does it say? Use calculator to graph f of x in question 4. Okay, and I think that looked like question 4, didn't it? Yeah. All right. Cool. Does it match? Yes. Last one. Write the graph of f of x equals the absolute value of 3x minus 5 as a piecewise function. Use your graphing calculator to verify the piecewisity of the function. Or is it the piecewiseness? None of the above. All right, this is like 20-1 stuff, right? Absolute value function. So what do we got to figure out? So when is it just 3x minus 5? Right? No absolute value. When is it just 3x minus 5? X. Okay, it's really x. It's really that expression, right? It's when the expression 3x minus 5 is greater than or equal to 0, right?
Yeah, 5/3.
5/3, yeah. So when x is greater than or equal to 5/3, because then this is going to be greater than or equal to 0, which means it's positive, so, okay. Otherwise, what do we say? It's like 2 math courses ago. Otherwise, we take the negative of it, right? Because we're only going to get negative values if what? X is less than 5/3, right? Well, I guess you can work it either way, right? I mean, just one has to be greater, you know, if the top is greater than and the bottom is less than or equal to, there's 0 at that point. Okay, so, do we want to verify this? Why not? Okay, calculator. Y equals clear. Okay, so what are we saying? It's 3x x minus 5 when x greater than or equal to, that's a 4, 5/3, and it's the negative, oops, no, let's leave with a bracket, negative of 3x minus 5, bracket, when x is less than 5/3, 5. Oh. Whew. Let's think. Nothing showing up. Okay, so there it is, right? And for comparison's sake, we could just, where's absolute value? Absolute value 3x minus 5. Oops.
It all gets covered in black.
Okay.